Hi everyone, this is week 6 and this week in the problem solving session we will cover finding absolute max min values of functions, and then we will talk about Rolle's theorem and mean value theorem. These are the content of this week. Let me start with a recall that will help us solving this first group of questions to find absolute max min of functions over a given closed interval. We will use closed interval technique. Okay, so if a function is given f of x, and if we want to find absolute max min of it, find absolute max min values of f of x over a closed interval. Let's say the statement of the question is like that. Which steps we should follow? Here are the steps. First, we will find critical points. Second, we will make a list of points, okay? Like, make a list of points consisting of, by the way, how do we find critical points of a function? We will compute first derivative equated 0, or we will look at the points where the first derivative is undefined. From these two, we will solve some points. Let's say we have x1 equals 0 is one of the critical points, and let's say, okay, let me fix it like this. Let's say x equals x1 makes the first derivative 0, and let's say x equals x2 is coming from the undefined part. After finding all those critical points, these are the critical points, we will make a list of points, okay, including critical points and also the endpoints. So, which list I am talking about? x1 and x2, these are coming from the critical ones, critical points. And then you will also add your list the endpoints of your interval. Okay, A and B. So also I am adding here A and B. They are coming from endpoints. And at all those points, you will evaluate your function. You will look at the images. x2, f of A, and f of B. And then from these images, you will choose the biggest and smallest one. Choose the biggest value as absolute max and choose the smallest one as absolute minimum value. Okay, that's how you will decide absolute maximum values of a given function over a closed interval. Okay, there are basically two steps. Find critical points and then make a list of points consisting of critical points and also the endpoints. Endpoints will be added to your list manually. Okay, so let's apply this technique on one of the questions in this group. Let's deal with this one. H of x is given like that, and the interval is given as -1 to 1. This function is a continuous function over this interval. That's why we can apply this closed interval technique that I reminded you in the recall. So we will start with finding critical points. Okay, let's do that quickly. We will compute the first derivative of the given function h. How do you take the derivative here? Of course, you will take the power down and you will subtract 1 from the power. After doing the simplifications, these are simplified, you will obtain this as the first derivative. Okay, so is there any point where h prime is 0 here? Look at the denominator. If h prime is 0, denominator should be 0, which is always -2. Impossible. So no point from here. And there's another part. Searching for critical points, you also need to check where h prime is undefined. Does this happen for some point? Look at the denominator. If x is 0, your function becomes undefined. So x is 0. This is the only critical point for us. Only critical point. Okay, first step is done. Now the second step, make a list. Second step, list of points. X equals 0 comes from the critical point. What are the endpoints of your interval? Here they are, -1 and 1. You will add them manually to your list. X equals 1, x equals -1. Okay. If endpoints are not, if they don't appear in your list, you will add them manually like that. Okay, this is critical point, and these two is added manually because they are the endpoints of your interval. Okay, now what should I do? I need to compute all the images under the given function h. h of 0, h of 1, and h of -1. Here is your h function. Okay, you can easily compute the images. H of 0 is -3 times 0 to the power this, of course, it is 0. -3, 1 times this, -3 and -1. Since this power is even, it becomes +1. Again, multiplied by -3, -3. And from this list of images now, you can see the highest and smallest value, right? This is the biggest value. Then it is absolute maximum value. I call it as absolute max. These two, both of them, same, smallest. That's why I will call them as absolute minimum value of this function. Okay? So you see this step. First step, find all critical points by searching for the first derivative zeros or undefined. Second step, make a list of all points consisting of critical and endpoints. Look at the images. And among the images, choose the biggest as the absolute one, choose the smallest as the absolute minimum value. Let's also draw the graph of this function to understand, to verify our computation. Okay, so let me draw the graph of it. Its graph goes like that. There's a cusp here. This is the graph of y equals -3x to the power 2/3. This was our h function, right? Okay, as you can see. And by the way, we need to concentrate over this interval. We don't want to see the graph over the whole real numbers. We just want to see it. We just want to find its absolute maximum and minimum value just over this interval, okay? And over this interval, as we can notice, this is the smallest possible value, which is 0, which we computed as 0 now. So we are verifying things now. This value 0 is the absolute minimum value. What are the absolute maximum values? They are here. You see, I am not exceeding the interval. I am just concentrating on the interval from -1 to +1. And at -1 and +1, your function attains the same value, which is -3. So these two are, as we computed above, absolute. By the way, this is not absolute mean, sorry. It is the highest value, absolute max. And these two are the smallest value of the graph, absolute mean. Okay? So this graph verifies our computation. Everything makes sense. Can I move on? Any questions from the classroom or from the Zoom meeting? Okay, let's continue with the next example in this group, ln x plus 1. Okay, this is 38. Let's solve the same type of question for this function. H of x is ln x plus 1. Okay, so let's start by finding critical points. First derivative of this function is 1 over x plus 1, right? So is first derivative function 0 at any point? Impossible, because numerator is 1. No point coming from here. Is it undefined for some point? Yes, look at the denominator. Denominator becomes 0 at x equals -1. By the way, the interval, there is also an interval given in the statement from 0 to 3. So look at your function, look at your critical point, -1. This is not included over this interval. That's why it is not a valid critical point. Not inside the interval. That's why we don't take it in our list, okay? You should always check whether the computed critical points are inside the interval given or not. If it is not inside, we are not taking it. Okay, second step, make a list of points. List. We cannot include any critical point in our list, but we have endpoints. We still have endpoints, right? X equals 0 and x equals 3. These are the endpoints of the given interval. And let's see the images. H of 0 and H of 3. Okay? What is H of 0? It is ln 0 plus 1. ln 1, what is ln 1? It is 0. I will draw the graph of ln function. You will see that it intersects x-axis at 1. H of 0 is ln 0 plus 3. Sorry, H of 3 is ln 0 plus 3. So ln 3. Okay, so in this list, I think 0 is the smallest value. So you can call it as absolute mean. And next, this value is the biggest. So we can call it now as absolute maximum value. Let me draw the graph so that everything makes sense for us. Do you remember the graph of ln x? It goes like that. This is the graph of ln x where it intersects at 1. But we need the graph of ln x plus 1. We can obtain the graph of it by shifting this graph. Let's take this graph 1 units left. By shifting, you can easily draw the graph of it like this. This is the point -1 now. So x-axis, y-axis, ln x plus 1. Okay? So what we have found, we are just interested over this interval from 0 to 3, this closed interval, right? You just look at the graph over this interval to see the highest and smallest value over this interval. As you can see, and as we find with our computations, this point is the smallest value, which is 0 here, absolute minimum value, and highest value is attained at the other endpoint. It is ln 1, absolute max, right? So our computation is verified with the graph. Can I move on? Is everything okay with this solution? Okay, let's move on. Maybe we can choose one more example from this group. Okay, let's choose one. Okay, this is also a nice one. 39. F of x is like that. One over x plus ln x. Over which interval? Over this one. 0.1 x 4. Okay, you can also write this interval as this one, right? It's the closed interval. We will try to find the absolute maximum of this continuous function over this closed interval. So we can use our technique. We will start by computing the critical points, okay? First, compute critical points. We need to compute the first derivative of this function. What is the derivative of 1 over x? You can see 1 over x as a power function like x to the power minus 1. So minus 1 comes down, you subtract 1 from the power, and derivative of ln is like that. After writing over a common denominator, you will have this. Now we are ready to search for where first derivative 0, where first derivative is undefined. First derivative is 0 when x is 1, right? And it is undefined when the denominator is 0, when x is 0. We have two critical points, but one of them is not included in the interval, right? This one is not in the given interval. That's why we are eliminating that one, but we will take this one on the critical. This is the critical point that we will write in our list. Okay, let's try to make a list now. Second step, our list of points. X equals 1 is one of the member coming from the critical point. Look at the endpoints. I will add now the endpoints manually. 1 over 2 and 4. Okay, x equals 1 over 2 and x equals 4. These are coming from the endpoints of the closed interval. Now I am ready to compute the images. F of 1, f of 1 half, and f of 4 I need to compute. What is f of 1? It is, here is your f function. You can easily compute the images. F of 1 is 1 plus ln 1, ln 1 is 0, 1. F of 1 half can easily be computed. Let me write this down. F of 1 half is 2 plus ln 1 half. This can be rewritten as ln 2 to the power minus 1. And then minus 1 can go down like this, minus ln 2. That's why I will write it as 2 minus ln 2. And finally, f of 4 is 4 times ln 2 to the power 2. Let's write 4 like that. And now you can take this power down. ln 4 is 4 times 4 plus, wait, let me see. Yes, 4 plus 2 ln 2. Okay, now from this list, what is the biggest? What is the smallest? I think this is the smallest one. So you can call it as absolute mean now. And this one is the biggest one. So we will call it as absolute maximum value of this function. Okay? So that's it. We applied the same technique for this function. Let me draw the graph so that you can also see the visualization of this problem. So the graph looks something like this. This point is the point 1 half. This point is the smallest, the point where we obtain the absolute minimum. And this point is 4. As you can see from the graph, this is the smallest value. So this is the absolute minimum attained at 1. And this is the highest value, right? Attained at 4. So this is absolute maximum value. We just concentrated over this interval. Right? We don't look at the whole graph. We just look at the graph of portion of the graph that corresponds over this interval. So there is an absolute mean, there is an absolute max. One of them is attained at the critical point. One of them is attained at the end point of the interval. Okay? So I think we can continue with the next example now, if no questions about this one. Any questions? Okay, let's move to the next one. This time we have this function y. We want to determine the critical points, and domain endpoints. Okay, let's do that. Let's start with the domain. Let me put a recall here. How do you understand the domain of ln type of functions? For example, you see this is the graph of ln function, and it is defined over which numbers? Where do you have the graph? Where do you have images? 1, but there are also lots of other values that we have the graph over them. For example, we don't have any graph here, right? Which means that ln x is not defined here. But for all the real numbers here, ln function is defined. So its domain is where x is greater than 0. Every time you have a ln function, you will look at the expression inside it. It should be greater than 0. Even at the 0, it is not defined because it diverges to minus infinity. Okay, also 0 is included at the not undefined points. So ln function, the domain of ln function is decided like this. So you can tell me now, what is the domain of ln x plus 1? You just need to make sure that x plus 1 is positive, right? So x is bigger than minus 1. This is the domain for the first part. Let's write this as an interval from minus 1 to infinity. Now, let's deal with arctangent. Be careful, this notation doesn't mean that 1 over tangent. It is the inverse tangent function, okay, arctangent. I will also recall you the graph of arctangent function, and you can directly see then the domain of it. If you know the graph, you know the domain, right? So its graph goes like, I think we drew this graph before in one of my lectures. This is y equals arctangent x function. This is pi over 2, and this point is minus pi over 2. So over which real numbers you see a graph, you see an image? Yes, for all real numbers, we have an image here, which shows that arctangent function is defined for every real number, okay? So the domain for this one is from minus infinity to plus infinity. In other words, whole real numbers, as it is seen from the graph. Okay, now we will deal with the domain of y. Y consists of two functions, right? ln part and the arctangent part. And now we know the domains of both of them separately, but for y functions, since we are using both of them, y function has to choose the x values for which both ln and arctangent is defined. So we will take the intersection, okay? So we will take the intersection of this with this, which is obviously this one because the other part is the whole part. Okay, domain of y is from minus 1 to infinity. Is this part okay? Domain part is like that. Now, we can start computing critical points. Okay, you see y function here. Let's take the first derivative. Derivative of ln x plus 1 is 1 over x plus 1 minus, what is the derivative rule for arctangent? We covered it last week, I guess. 1 over 1 plus x squared. Okay, this is the derivation rule for arctangent. Okay, this is the first derivative function. You can write it over a common denominator easily. 1 plus x squared minus 1 minus x. And then this is the common denominator. We have simplifications, as you can see. So the most compact form of the first derivative function goes like that. Like this, okay? And now we can search for where it is 0, where it is undefined. Okay, this first derivative function is 0 when we have, I think, 2 points. When x equals 0 and x equals 1. This first derivative function is undefined when x is, look at the denominator, choose the points that makes it 0. Minus 1. And from here, since we can never have some square is minus 1, no point comes from there. Right? Okay. So x is 0, x is 1, x is minus 1. These are the critical points. Okay, let's also try to find out what is the absolute max and absolute mean of this function, right? Let's complete also that part. Second part, you make a complete list of critical points and endpoints. And I want to pay special attention to this part, please. The domain, the interval of this function is like that. We will be using the domain interval, okay? It is not a closed interval anymore. In all the previous examples, the interval was closed. Now it is an open interval. Open means like excluding the endpoints, not including, right? Open. Still, you will add the endpoints to your list. By the way, I think since this is not included in the domain, you see -1 is not included in the domain, we shouldn't take this as a critical point. Okay, not in the domain. Okay, I will just remove it from my list, but it appears as an endpoint. So if the interval is open, you won't write the endpoints like this, but instead, since they are not included, we cannot say x is -1, x is infinite. Instead, we will write in the limiting position, okay? We should still check the endpoints, what happens at the endpoints, but since they are not included, we will check it like this. When x approaches the -1, when x approaches the infinity. By the way, you should approach -1 inside the interval, meaning that from right direction. Okay, so we are ready to find out what happens to the images. F of 1, our function was y function. Let's use y notation. Y of 1 at 0. Okay, y of 0, y of 1. And for these two, we will write limits. Limit as x goes to -1 from right of y function. Okay, let's write 1. And for this, limit as x goes to infinity of y function. What is y of 0? ln, okay, we know the expression of our function ln. This plus arctangent 0. ln 1 is 0. What is arctangent 0? Look at the graph. Arctangent 0 is 0, right? At the origin. The graph of arctangent function tells us that this is also 0. Okay? Y of 1. ln 1 plus 1 plus arctangent 1. Okay, this is ln 2. What is arctangent 1? Tell me a function, tell me an angle whose tangent value is 1. You can read arctangent values like that. Guess the angle whose tangent is 1. 45 degrees, right? So this is pi over 4. You can read arctangent values like this. Okay, then I am ready to compute these limits. This is limit as x goes to -1 from right, ln x plus 1 plus arctangent -1. Okay. So what about those limits? If you insert -1 inside ln, you kind of obtain ln 0. What happens to ln function around 0? Look at here, please. What is ln 0 from right? This part tells you what happens to ln function if you approach to 0 from right. It diverges to -infinity, you see from the graph? So this part goes to -infinity if x goes to 1 from right. -infinity. So this is a finite value. Whatever it is, it's a finite value. By the way, it is -45. But minus pi over 4. Okay, so the result is -infinite. And let's compute the last limit. Limit as x goes to infinity, ln x plus 1 plus arctangent x. What is ln infinite? Graph? ln infinite is infinity, right? It's always increasing. So this part is infinite. So the result is infinite. Okay. After seeing these images, now we should be ready to tell whether this function has an absolute max or min. What do you think? The smallest value is minus infinite. The highest, the biggest value is plus infinite. What does this mean? Does this function has an absolute minimum value or an absolute maximum value?
Absolute has max,
Also for absolute max, it is infinite. So infinite can never be attained, right? That's why the absolute minimum value can never be attained, minus infinite. Absolute maximum value, we can never reach it. We can never attain it. So we will conclude no absolute max, no absolute min. Okay? They both can not be attained. Okay. No absolute min because minus infinity can never be attained. No absolute max. So this example is a nice one because, first of all, its interval is open. That's why we use limiting notations at the endpoints. Second of all, no absolute max, no absolute min values are attained. Okay? Any questions? If no questions, I want to continue with the next example. Okay, I move on then. Let's look at this one before the break, and then we will take a 10 minutes break or 15 minutes break. Okay, the question is, find critical points. Find critical points and domain endpoints for functions. Then find the extreme values, absolute max and min. By extreme values means absolute max or absolute min, okay? But this time our function is a bit different. It is a piecewise defined function. For this type of functions, okay, we will again follow the same strategy like we first find critical points, and then we will make a list to decide if we can see the highest and smallest value. But how can we find the critical points for piecewise defined function? Of course, we will start by taking the first derivative. The first derivative function will also be a piecewise defined function, obviously. So x is less than 1, x is greater than 1. Be careful. I want you to notice something. I didn't include 1 here. Okay? So I don't put equality sign there. I will just read x equals 1 separately. This is what you should do for piecewise defined functions. For x equals 1, which is the breaking point of this function, which is a special point of this function, should be analyzed separately. We should pay special attention to this point. But except x equals 1, for this one, we will do more analysis soon. But except it, you can just take the take the derivatives of those polynomials. The derivative of this polynomial is minus 2x minus 2. I am just applying the derivation rules. Derivative of the next polynomial is minus 2x plus 6. So these are the first derivative functions for x is less than 1 and for x is greater than 1. What about x equals 1? Please, I warn you, you cannot just include x equals 1 here. This is not correct. You will see soon that this function does not have its first derivative for x equals 1. If you put equality sign there, you will just do this mistake. You will just get caught with the trap. You shouldn't put equality there. Okay, for x equals 1, our aim is to understand if this function y prime is, okay, let's put a question here. Is y prime defined at 1? So we want to answer this question. You cannot just include it there. I want you. This point needs special attention because it is the breaking point. So for this one, you will compare the left-hand derivative and right-hand derivative. So what I mean is you will check whether the derivative function at the left side and the first derivative function at the right side of 1 are equal or not. Just like checking the continuity. Do you remember how do we check continuity? We were looking such limits for the original function itself. But here I use the first derivative function. This is how we can check whether a function is differentiable or not at the breaking point. This part is called left-hand side derivative. This part is called right-hand side derivative. If they are equal, then we will conclude that this function is differentiable at 1 and the value is that given value with the limit. Okay? If they are not equal, we will say that first derivative function is not defined at 1. Okay, so what happens to y prime on the left side of 1? So I will take this equation, left side. Minus 2x minus 2. What happens on the right side? Minus 2x plus 6, right? So let's compute the limits. You will just insert 1 for x. Insert 1 for x, this is minus 4. Insert 1 for x, this is plus 4. You see? They are different. So the conclusion here is y prime is not defined for x equals 1, okay? Don't forget, I warn you 5th time. For the breaking point of piecewise defined function, you should analyze for x equals 1, which is the special point of this function. You should pay special attention. You should do this analysis. And this is not a difficult analysis. Just compare the left-hand side derivative, right-hand side derivative. If they are equal, you will conclude y prime is defined. If they are not the same, y prime is not defined there. Okay. Let me ask you a crucial question now. If first derivative function is not defined at some point, then what can you say about x equals 1 in terms of whether it's being critical point or not? Is it a critical point? Okay, how do we find critical points of a given function? So let's now search for the critical points. Okay, so you look at the first derivative function, right? For x less than 1, the first derivative is given like that. You equate it to 0. And from here, you solve x equals minus 1. For x greater than 1, you take the expression. First derivative function is given like that. And you solve for the point. There is also one more thing that you should check to make a complete list of critical points. Is there any point where first derivative is undefined? Yeah, we find that at x equals 1, first derivative is undefined. So x equals 1 is also a critical point, okay? So we have 3 critical points here. Critical points. X equals minus 1, x equals 3. These are coming from where? From the part y prime is 0. Also, x equals 1, and this comes from where y prime is undefined. Now, it's all clear, right? We have 3 critical points. Okay, after finding the critical points, we will look at the images and find absolute max-min values. This is the last step. So, our list consists of 3 critical points, right? By the way, what is the domain of this function? Look at the expression. It is defined for all real numbers without any exception, right? X is less than or equal to 1, definition is given. X is greater than 1, definition is given. So the domain is all real numbers, yes, everywhere. Okay, so why do we need the domain? Because we will also take the domain endpoints to my list. That's why I emphasize the domain. Okay, critical points, x equals minus 1, x equals 3, x equals 1. These 3 are coming from the critical points and domain endpoints, right? X goes to plus infinity, x goes to minus infinity. As it is an open interval, we are using limit notation. Okay, now the images. Y at minus 1. You can easily compute y function at minus 1. You will find image like this. Y at 3 is also 5. Y at 1 is 1. Now limit. Limit as x goes to infinity of y x. Since x goes to infinity is bigger than 1, I will take this part of the function. Minus x squared minus 2x plus 4. Minus x squared minus 2x plus 4. What is this limit? If you insert x equals infinity, because of the minus coefficient in front, it is minus infinity. Let's also compute the other limit. Minus infinity of yx. This time I will take the other expression as x goes to minus infinity. It is less than 1. So I will take minus x squared minus... wait, I think I took the wrong... Yes, here, this should be the other one. Because x is greater than 1. Plus 6x minus 4. Okay, let's fix it. And this part should be the... Right? And this is plus 4. Okay. And what is the limit here? Minus infinity. Nothing changed, right? Because of the minus coefficient, it is again minus infinity. So, among all those numbers, what is the biggest? What is the smallest? I think biggest one is here. So I can name it as absolute max. There's an absolute maximum value of this function. Is there an absolute min? Since minus infinity can never be attained, you will say that no absolute minimum value. Okay, this is the end of computation, but I also want to draw the graph of it just to make sure that everything is verified and you see the visualization of the solution. The graph of this function goes like that. It is a strange graph, but this point is minus 1, and the image is 5, as we computed there. This point is 3, image is 5 again, which is the highest value of our graph, you see. These two are absolute maximum value. And is there an absolute min? By the way, this is also another critical point, which is 1. Why we find that at this point our function, first derivative function, is undefined? Why this function is not differentiable at x equals 1? It is defined there, but it is not differentiable there. Because there is a corner there. Because there is a corner here. We covered this last week, remember? It is not differentiable at x equals 1. See, everything makes sense. And you see, no absolute mean, because it keeps decreasing and decreasing. Okay? I think we should stop here.